Thank you for following on from parts 1 and 2, which hopefully scoped the challenge and whetted your appetite with some of the new and emerging technologies. In this third part, I will detail and critique some possible scenarios for our energy future. As we have already discussed, we need to address supply, use, and as importantly, distribution and storage of energy. As we have seen, some of these technologies offer improved efficiency while others provide more flexibility. Many technologies already exist, but the real uncertainties are in scale up and deployment. But we all are looking for cheap, convenient, and now clean energy. Turning to the first key driver, we've already noted that today's energy utilization is far from efficient. And many reporters have commented on how new technologies can improve this through electrification, harnessing renewable energy. In their reports, the UK Committee for Climate Change has provided some excellent summaries on two specific opportunities: electric vehicles and heat pumps. These charts demonstrate their efficiency benefits. Using renewable energy, electric vehicles double efficiency over petrol cars, while heat pumps significantly reduce energy requirements for our buildings. Today, electrification offers significant energy efficiency improvements, but the cost of deployment is still high and requires wider customer acceptance. Let us take these new technologies into our first future energy scenario, which uses the block model we used in the first video, and it considers full electrification. Many stakeholders favour this scenario, which utilises renewable energy, such as solar and wind with batteries. It maximises the use of electricity for transportation with electric vehicles, and within our homes it considers heat pumps deployed with smart controls technology. This scenario sees optimal energy use, halving our total demand, going from the 6 units I showed in video number 1 to 3 units here. The recent BBC Energy and Net Zero America reports estimate that this scenario will require a tripling of our electricity grid, though this could possibly be tailored if we were successfully decentralize some of our supplies. To meet this demand, though, we would have to scale up our current renewable energy supplies by a factor of, say, 8. This will require very significant expansion on current plans with associated concerns on land and coastal water usage. For this scenario to work, the seasonality of power supplies and demand will have to be supported by enhanced smart control systems, battery and power banks, and with significantly higher levels of building insulation. While offering a rosy outlook, this scenario does raise a number of concerns. How difficult will it be to scale up the renewable resources? What will be the costs for grid expansion and customer home improvements? How will we manage energy security, and how can we manage the implementation risks associated with the deployment of millions of heat pumps? Can we successfully convert our industrial, aviation and shipping sectors? All good questions, but let us embrace electrification by awarding it with a gold standard to solve our energy transition. To address some of these concerns, though, let us turn to our second key driver, flexibility. Today, we import energy from overseas, and as we move forward, it is still doubtful that we will be able to generate sufficient electricity to meet all our daily demands throughout the year locally. Technologies such as green hydrogen and biofuels are being developed to try and address these flexibility needs. Associated technologies include the conversion of hydrogen to ammonia, which potentially can be transported more easily. Green hydrogen, ammonia, and biofuels provide an opportunity to commoditize and move our energy into the future. We can bring these energy vectors into our second scenario, a hybrid solution, incorporating the benefits of these more flexible fuels onto our electrification scenario. This would still be underpinned by the efficiency of electrification. Both domestic and transport sectors can benefit from hydrogen through fuel cell vehicles, and hydrogen boilers to meet our heavy-duty and seasonal demands. These measures will reduce the extent of electricity grid expansion, especially as our current gas grids can be repurposed. Overall, this scenario will require more renewables to facilitate the production of green hydrogen from electrolysis. However, potentially this can be realized at locations with lower cost and with more reliable renewable energy resources. For instance, this could be from North Africa or Australia with pipelines and/or shipping connecting resources to energy markets. This scenario with hydrogen and biofuels also provides a more feasible solution for the shipping and aviation sectors. And indeed, the German energy strategy considers green hydrogen being used for the manufacture of feedstocks for the chemical industry. This hybrid scenario requires a small premium on costs and efficiency to provide flexibility for a more sustainable energy future. Furthermore, it allows a realistic expansion of our power grids. However, given power needs will take priority and technology challenges to bring green hydrogen and ammonia to the wider market are significant, this option also carries deployment risks to achieve our 2050 goals. However, this scenario brings 1 gold and 2 silver standard technologies to bear. To help us understand these deployment risks, we can expand our earlier system model by adding scale-up and deployment challenges such as design and installation. The critical success factors for technology deployment are innovation, finance and environmental impact, human resources, project management, and safety. Looking at this model in the round, I will conclude that the degree of change required during the energy transition is very significant, particularly within the time available to 2050. So while target setting is easy, delivery of a plan is far more uncertain and challenging, and hence the subtitle for these presentations, Efficiency, Flexibility and Uncertainty. To manage these uncertainties, I believe we need to broaden the range of technologies which can be deployed, and especially look at those which can be capitalized on the current infrastructure, available skills, and consumer familiarity. Here we can consider the conversion of our gas grids to hydrogen service, the deployment of hydrogen-ready gas boilers, and industry's experience with hydrogen production and carbon dioxide removal. Blue hydrogen and carbon capture utilization and storage provide a parallel but mutually beneficial track to electrification to achieve net zero. We can bring these into a third scenario, the interim hybrid scenario, one which can reduce the risks of achieving net zero by 2050. Clearly, again, we still need to pursue the electrification technologies with, say, a doubling of the power grid, but this time over a more realistic time period and with a better phasing of renewable scale-up. Our gas grids are still repurposed to hydrogen service, though with greater surety of early hydrogen supplies, which over the next 20 to 30 years can be produced more cheaply than that from electrolysis. Blue hydrogen schemes are already being considered in the UK, the Netherlands and Australia. This scenario reduces the uncertainties on the full deployment of renewable energy, green hydrogen and biofuel technologies. It is estimated that blue hydrogen will double the cost of its source natural gas, though this is still less than the 3-to-1 premium we pay for today's power. This scenario provides an effective segue to the sustainable full hybrid scenario. It is delivered through 1 gold, 2 silver and 2 bronze standard sets of technologies. Having looked at this picture within the UK or the developed world, let us look back again at the wider picture for the developing economies, where we identified a different set of priorities. We discussed this in part 1. We can also place their different strategies onto our energy system model as shown here. Simply put, we need to manage the challenges and impact of energy flexibility for the developed nations, while simultaneously increasing energy supplies to developing countries through deployment of gold standard efficiency technologies. This is consistent with many of the energy initiatives in developing countries, which are looking at electrification, and I provide a couple of examples here, including the development of this large solar power project at the Zatari refugee camp in Jordan, and the SAIC low-cost electric car in China. Now let me move our scenarios into the reinforcing multi-vector ring schematic I used in the first video as well. We have seen today that we are in the gas-centric world still supported by oil and coal. Moving forward, we need to rapidly move to a renewable-centric world. As I have explained, I believe we could deliver an interim hybrid solution using all three sets of technologies by 2050 to achieve net zero. However, our longer-term goal will be to phase out blue hydrogen and carbon capture as these get replaced by biofuels, green hydrogen, and ammonia to meet all our flexibility needs under a full hybrid scenario. This must be the goal for 2100, though hopefully a lot earlier. So 2050 is only part of our journey. However, it can still be carbon neutral. With the growth in consumer demand forecast by the IEA to double by 2050 and to grow further by 2100, we will also see the need for extensive efficiency measures. Let me now translate this plan and color code it against our gold, silver, and bronze standard technologies, as hopefully this will clarify our transition trajectory. Gold standard technologies dominate to ensure efficiency. These are supported by silver standard technologies to provide flexibility, while bronze standard technologies are used to manage uncertainties during the challenging transition period. You will have seen that some oil and gas will still be utilized in 2050. Like others, I assume that this will be offset through other measures such as reforestation, which I hope consider here to be a further bronze transitional technology. Hopefully this chart again shows the reinforcing nature of our different energy vectors.
So let me now summarize my conclusions for our policymakers. Firstly, something obvious. Today we rely on cheap and convenient energy, so our move to clean energy will be challenging and requires firm policies. Renewable energy, electric vehicles and heat pumps will ensure efficiency and ultimately reduce costs. Consequently, we must rapidly maximize deployment of our gold standard technologies. However, we will still require flexibility to meet the demands of a global energy market. We need more than batteries, and we will still need to transport and store energy. To deliver this flexibility, we must deploy our silver standard technologies. With the tight timeline to 2050 and significant delivery exposure, I contend that we must also deploy our bronze standard technologies. I would also surmise that there is limited regret from implementing these, as their deployment can be reduced at any time as they bridge to our longer-term solution. As you have seen, these conclusions build up to form our target board for a gold, silver and bronze transition plan. We can only deliver this program through fostering strong cross-sector and international collaboration and developing an effective communication plan for the benefit of all stakeholders. To really highlight how this plan is price sensitive, this IEA chart highlights the hydrogen price at which certain sectors become cost competitive for the new fuel. I hope this presentation has provided some food for thought and clarity on the what behind our energy transition scenarios. Please continue with the final part 4 of the story, which looks at some aspects of delivering the plan, the how, and concludes with a number of recommendations for our policymakers for our energy transition. Thank you.